Hello, I'm George Jenkinson and I'm going to talk to you about our paper Braille-tip, a structured small footprint tactile sensor for high acuity dynamic tactile tasks. Learning to read Braille can be difficult, partly because independent practice is difficult for beginners. Braille-tip is a handheld tactile device aimed at helping people learn to read Braille independently. The overall purpose of the device is to convert tactile Braille signals into text that can be digitally stored for later recall or to be read out immediately. The system is based on a soft elastomeric membrane with taxels whose dimensions and layout match Braille text. Physical disturbances on the membrane are hydraulically translocated to an array of liquid channels. Computer vision is used to track the changes in each of these channels and attribute it to a compression of the relevant taxel. This can reproduce the shape of small objects when the membrane is pressed against them. This builds upon a transduction mechanism that we've explored in more detail in our previous work. If passed over Braille letters, the order of taxel stimulation can be used to detect the presence of raised Braille dots. Here, the dot stimulates the sensitive channels going from right to left, or red, then green, then blue. 13 sets of trials where Braille-tip was passed over 4 Braille dots were used to calibrate when a peak relates to a Braille dot for each taxel, only considering numerical peaks that reach a value of above 0.4 or 40% of its maximum value. An algorithm was able to correctly identify 4 and only 4 peaks in each of the 13 trials. Reading a word means that Braille-tip needs to break the signal into separate characters. The signal from passing Braille-tip over Braille text is converted to binary using the threshold just defined. The Braille-tip itself is split into taxels, here labeled to be grid-like for ease of explanation. The synchronization and taxel layout is key to how Braille-tip works. 2 signals that are close enough that they both occur before the next taxel in the row is stimulated must be close enough to be within the same letter cell, as you can see in the green row with the blue square around it. If they occur further apart than this, then the later one is the start of the next letter, as in the red row at the top. The taxels within a column are then synchronized so that further signals can be assigned to the next letter, and this process is repeated. If we look at the signals in just a single column, here column A, we can see that they closely mimic the actual layout of the Braille dots themselves. The other columns B and C are like backups, so that in case one is wrong, the other 2 may compensate. This mimics how many people read Braille using more than just one finger. In this example, the word text in Braille is converted to a binary by Braille-tip, which can then be read aloud by a computer.
Text.
This work demonstrates that we can use a basic algorithm to achieve good results. In the future, we may discover that it's more effective to develop a more complex algorithm, and changing transduction mechanisms from something that uses a camera is likely to save a lot of physical space. Making a device as portable as possible is likely to be beneficial to end users in the real world. Soon, this should be tested with the intended group of end users to see whether it's a genuinely useful device and to guide any future developments.